Okay, students, so we'll move on to the next topic, that is stack and queues. Fine. So you may be feeling like why we need to study stack and queues while we are discussing about the assembly language programs. Okay, so here we are depending over a stack if you want to execute the concept of subroutine. Okay, so in the next class we are going to discuss about a topic called as a subroutine, where we are successfully utilizing the stack concept. Okay, so we need to study or we need to glance, okay, like how the push operation and pop operation will be performed by the stack. Clear? Okay, so we'll go through this stack and queues. So we are studying about stack as well as a queues exactly. Okay, but here in our syllabus we are utilizing the concept of stack exactly. Okay, when we are comparing the stack and queues, the complexities are more when it comes for the queues. Okay, we'll discuss it. Okay, what complexity we are finding over here. Okay, in this today's session, we are going to discuss. Okay, so stack and queues. So computer program need to perform some subtasks using subroutine structure. Okay, to link main program and subprogram, we use data structure called stack. Okay, you may be asking like what exactly subroutine stand for. Okay, so I told you beginning like we are going to discuss about the topic called as a subroutine in the next class. Okay, first I would like to give some brief introduction about a concept of subroutine. Okay, so in depth we will discuss in next topic. Okay, or else next class. Fine. So just consider a person. Okay, so he wake up in the morning at 7 o'clock. Then later he may go for daily jogging and all. Okay, so that is what his daily routine exactly. Okay, then he will come back from the jogging and he will have his breakfast. Okay, then he will go to college. Okay, he will attend the classes. Okay, afternoon again lunch. Fine. Then afternoon labs and all. Okay, then he will come back to home. Right. So this is what we can call it like a daily routine of a student. Right. Okay. But in between, if you bunk the class of, or else if you bunk the class in the afternoon session and if you go for a movie, okay, then we are calling it as a sub-routine, okay, which is not continuous, okay, which is not regular, okay. But in between, what we do, we are performing some other task over there. Okay, the main task was attending the class, okay, but we are suspending the task, okay, and we are concentrating on some other subtask exactly. Okay, those subtasks we are not achieving regularly. Remember, okay, like daily we won't go for the movie, is it right? Okay, then he will get an attendance shortage. Is it fine? College will charge him a heavy fine, right? Okay, so sub routine means okay, morning to evening. Okay, some kind of routine will be adopted by a student. In between, some day, okay, he will perform some other task. Fine. So that other task we are calling it as subroutine. Likewise, in our like computer organization also, okay, we are considering it as main program and subprograms. Fine. Your processor will be continuously keep on executing the daily routine. Fine. Like when we are like switching on our system to till shut down our system. Okay. So between that, there will be a daily routine. Okay, continuous. Okay, the normal work will be available. That we are calling it as the main program. Okay. So in between that, okay, it may be the request of a user, it may be the request of any hardware or a software, fine. So they are expecting some services from the processor. So this main daily routine task will be paused, okay, for some duration, and your processor will start providing a service for that subtask exactly, the request for the subtask. Fine. So here we are using the concept of stack for only one reason. Remember, students, if you want to suspend the execution of main program and if you want to transfer the execution control to the sub program, then what we need to do? We need to mention somewhere the return address for the main program from the sub program. Yeah. Okay. For your better understanding sake, let me write this picture or representation. Consider this is what a main program and this is what a subprogram. Okay, this is what a subprogram, and here we got a processor. Okay, so he will be always executing this main program. Okay, and in between, sometimes you may get a request from a subprogram to execute. Right? During that, what processor will do is processor will pause the execution of this particular main program. The execution control will be transferred to the subprogram. Fine. The complete execution of subprogram will be done. Fine. Finally, the execution control from the subprogram to main program, it will be shifted by your processor. Okay. So here, what we are expecting is return address to this main program. Observe it. In case of main program, if we are having total four different lines, okay, main program is consisting of four different lines. Okay, when the processor is busy with executing this four line of instruction, okay, consider like it is executing a instruction which is located in a line number 2. Okay, so in this position, okay, your processor is finding a subroutine request from other program. Fine. Then your execution control from main program, it will be transferred to the subprogram, right? Fine. So how many lines you are executed already? Two lines. Okay. So if I want to begin with the execution of main program again, I should not start from the beginning. Remember. Okay. Till here we already executed, right? So before this, whatever the variables we got, okay, they are already residing with some original values over there. Okay. Result of some computation, right? Okay. So it should not be overrated by any other value. So what we need to do? Fine. So to this particular position, we need to set some return address so that when we are getting a control of execution from subprogram to main program, we should begin our execution from a new line. Remember this. So this we are calling it as a return address. Fine. You are already executed this particular second line. So in the next, what we need to do, we need to execute the third one. So this third one instruction address, what we have, this we are managing inside a location, right? That is what we are calling it as a stack. Clear? That is what we are calling it as stack exactly. Got some idea? Main program we have, subprogram we have. Subprogram will request for some service from a processor. So the execution of main program will be halted. Fine. The execution control will be shifted from main program to the subprogram. Meanwhile, till where you are already executed this main instruction, main program, okay. So the next instruction address, whatever we have, that should be stored in a stack exactly. So after completion, some X, okay, consider it as X is the address where we want to return it to the main memory, sorry, main program exactly. So after execution of complete this program, okay, your processor will just go through the stack where exactly that return address is stored. Fine, he will get the return address from where the execution should begin. So that is pointing for this particular third line. So from third line, the main program execution begin exactly. Fine. So this is what the concept of subroutine is. Okay. For storing this return address, we are using a stack. You may ask, like, why we need to go for a stack? Why can't we use any variable? Okay, so the processor can refer that variable, right? Here we got one more topic called as nested subroutine. If you are having only one subroutine, then okay, fine. Fine. How we had nested functions, right? Okay, function is calling for another function. Okay, inside a function, it will call another function, right? In such cases, we need to maintain multiple return addresses. Okay, so variable is not sufficient for managing and for handling the multiple return addresses over here. So we are dependent on stack exactly. I hope you got the complete idea what exactly subroutine is and how you are utilizing this stack concept in case of subroutine. This is very basic. So in next class, we are going to discuss in deep about the subroutine. Yeah? Okay, fine. So stack is a list of data elements, usually words or bytes. Okay, with access restriction that elements can be added or removed from one end of the list. That is LIFO, last in, first out. Okay, so here you got one sample of stack. Okay, a stack of word in the memory, the name of this figure. Fine. So out of our memory itself, okay, some piece of memory we are considering it as a stack. Fine. So here we are mentioning it as bottom of the stack and top of the stack. Remember, okay. So in this case, like current top is pointing for -28. Fine. The second top is like 17, later 739. Okay. The bottom element is 43. Okay. You can observe. So this we are considering it as a stack. Then the bottommost element we are naming it as bottom. The topmost element, whatever we are having, that is pointed out by using SP. The full form of SP is stack pointer. Okay, or else we also call it as stack pointer register. Okay, how we are having general purpose register, we are having a dedicated register which we are calling it as a stack pointer register, who will be always pointing for the top of the stack. Clear? So whatever if I want to enter, okay, we feel that it is a empty stack. So first we are entering over here, later next. Okay. So wherever your stack pointer will be pointing for, okay, to that address, you are going to push the content. Okay. wherever your stack pointer is pointing for, okay, from that or from that location, you are going to pop. Okay, so SP we are using it as a reference. Okay, so that we can perform push and pop operation. Wherever SP will be pointing for, find a memory location. There we are uploading the content in case of the push operation. Okay, in case of pop operation, wherever SP is pointing for, from there we are popping the element from that particular stack exactly. Fine. So we'll go through that. So here, stack operation, when it comes for stack operation, we got two varieties. One is push operation and the second one is pop operation. Okay. So out of this figure, we can also observe the stack top. Okay. Like current top element. So this is what the stack top, according to this figure, the current top or else stack top we call it as. Then bottom of the stack, bottom stack we call it, or the bottom element also we call it as. And later, stack pointer. Okay, in our program, in our further program, in case of subroutine, if we mention SP, capital SP, that means that stack pointer. Here, stack pointer is always pointing for the top of the stack. Remember, okay, stack pointer will be always pointing for top of the stack. Okay, see, if you are having empty stack, your stack pointer will be pointing for this particular location. Okay, if it is full, then it will be pointing for this particular location. Remember this. Clear? Okay, fine. So I hope you got some brief idea about what exactly stack stands for. Okay, what is stack pointer, what is current top of the element and bottom of the element. Okay, so here we got some code, okay, which is explaining the working of push and pop operation. Okay, so two-line code we got. Okay, this can be compressed, minimized into single line also. We'll see this how it will be. Fine. Okay, let me draw a stack representation over here. Okay, so feel that this is what the stack. Fine. So these are the stack element location. Fine. Let me name it as 0, 4, 8, and 12. Okay. So feel that this is an empty stack. Okay. So your stack pointer is pointing for this particular location. Fine. This is what the bottom and this is what the topmost. Okay. Topmost element of the stack. But remember, when you are entering one value, okay, one value for this empty stack, so this will become bottom and also the top of the stack if it is having only one element. If you are entering second element, bottom will be this one, top will be this one. After entering the third element, top will be the 4, okay, bottom will be the 12. Clear? Okay, fine. So for this particular explanation, like push operation, okay, just observe subtract hash 4 comma sp. Sp we have already, no problem. Okay. Then later, move new item. Okay, move new item. Let me name this new item. Okay, and I am going to write it as, okay, somewhere, some variable we are having, consider like some memory location which is labeled as a new item. Okay, so that is equal to 100. Example, 100 rupees. Okay, so now, actually, okay, if it is empty, your stack pointer, sorry for, like I told you, right, this will be pointing for 12, I told. Okay, so remember, if it is empty, your stack pointer will be pointing for 16 exactly. Okay, SP will be pointing for 16 exactly. When you are trying to enter some value, fine, if you are trying to enter some value, then what operation we need to perform? See here, subtract hash 4. See, I want to enter some value for, bottom of the stack, where we have a bottom of the stack beginning from 12, right? Okay, so initially your stack pointer will be pointing for 16 exactly. Okay, initially stack pointer will be pointing for 16 exactly. Why? Because when we are discussing the pop operation, you will get to know. Okay, after popping each and every content of the stack, okay, this will be subtracted with, this will be added with 4. So stack pointer will be pointing for 16 exactly when it is empty. Okay, I tell you later how it will be. Okay, now consider stack pointer is pointing for 16. Okay, your stack is beginning with, like we want to consider from 0 to 12. So 12 we are considering it as bottom of the stack. Clear? Okay. So now, if I want to insert any particular value for this particular location, okay, stack pointer is pointing for 16, right? Then what I need to do, I need to subtract it by 4 so that stack pointer can be updated to a location called as a 12. Okay. So to this particular location 12, I need to shift the content of new item, which is equal to 100, right? Same thing we are performing. See, if I want to perform a push operation for this empty stack, subtract hash 4 comma sp. If I perform this, sp is pointing for 12. Okay, 12 is equal, sorry, sp is pointing for 16 exactly. Sorry, sp is pointing for 16 exactly. So 16 minus 4, it will be pointing for 60. It will be pointing for 12 now, right? sp is pointing for 12 now. Okay. So later, what I need to do, see, this is how we are updating our stack pointer. Next, move new item comma sp within a bracket. Observe it carefully. Move new item comma sp within a bracket. What does it mean? If you are representing any variable, any register within a bracket or any label within a bracket, okay, that should be considered as a address. Okay, the value of that particular register should be considered as an address. What addressing mode we are using? Indirect addressing mode we are using over here. So students, so SP is equal to 12 now. So 12, if I consider it as an address, okay, where it is located? Here it is. Okay, so inside that, I need to move the value of new item that is equal to 100. So here we are uploading 100 over here. Yeah. So if I want to perform one more operation, again I need to subtract it by 4 so that I can point it for top of the element, top of the stack. Okay. So whatever we are entering for the stack, that should be made as a top. Okay. So this is bottom right now. So the next, after entering some value for this particular location, let it be like 98. Okay. So this will be called as a top. Right. Okay. You already know about this stack concept symbol, right? Later, after entering the fourth element, so here again subtraction. So SP was pointing for this particular location. After subtracting it by 4, SP will be pointing for again this 4. So here 56, let it be 56. Then again subtracted by 4, your stack pointer will be pointing for this particular location. And if I want to upload like 23, okay. So now your top of the stack will be pointing for a location called as a 0, which is holding a value which is equal to 23. So this is what the top. Okay. Over this, if you try to upload or if you try to push some element, then you will be getting an error message over there. In next slide, we are going to discuss about empty error and overflow, how to avoid this kind of empty error and overflow error. Okay. So we'll see that. Now, for the same stack, fine. If we are uh, if we are trying to pop, okay. So now pop operation, we'll see this. So your stack pointer is pointing for where exactly? It is pointing for 0 exactly, right? It is pointing for 0 exactly, right? So this is what the current status of our stack exactly. So now, if I want to begin with the pop operation, okay, till I find the empty, okay, I want to pop it out, okay. So now, see, move SP within a bracket from item. Where we have item, see, I'm naming it as item is equal to somewhere. Okay, item is equal to some particular memory location. We are labeling it as item exactly. Okay, so whatever the stack pointer is pointing for, okay, so that should be shifted to a location called as item. Okay, so now stack pointer is pointing for where exactly? 0 exactly, right? So SP within a bracket means what? 0 should be considered as the address. If I consider 0 as the address, so instead that what value we have? 23 we have. So 23 will be shifted to 23 will be shifted to location called as item. Okay. So now what I need to do, I need to release this stack location, right? I need to release this stack location. How we can do that? Okay. So what we need to do, we need to update, remember, we need to update our stack pointer, which was pointing for 0 to 4 exactly. Okay. So that the top of the stack can be updated to the next value. Clear? So previously it was pointing for 23. We already popped it out, right? Next it will be pointing for next element. Okay, so what we need to do, we need to update our stack pointer. Okay, fine, we'll see this. Again, we need to perform what we need to perform. See how it will be pointing for this 4. Okay, add hash 4 comma sp. What was sp pointing for previously? Sp was pointing for 0 exactly. Add hash 4 comma sp will update our stack pointer from 0 to 4 exactly. Is it right? Sp was pointing for 0. 0 plus 4 exactly. Then sp will be pointing for 4 now. So what is the value residing? 56. So if you try to pop, then 56 will be popped out in the next cycle. So now we'll see this. Okay, next cycle, observe it. Okay, so we'll consider one more. Okay, instead of this item, let me consider it as some other label name. Okay, let it be like new item itself. Okay, or as any other XYZ, let it be XYZ. Okay, so whatever the label we are mentioning here, also it should be mentioned with the same. Okay, don't get confused. Your item is nothing but XYZ. Okay, for the second value, I am taking it as just for the reference. Okay, so now again move SP within a bracket comma item, that is nothing but XYZ. Okay, then again you need to perform add hash code for SP. So continuously, you are going to pop the element from the stack, right? First time you are popping the first element, second time second, third one, third time third one, fourth time fourth one. Okay. After popping, just observe, after popping the 100, okay, that is at a location 12, again we need to add hash code for SP, right? This is what the complete operation of a pop operation. Because of this, your stack pointer will be pointing for 16 exactly. Okay, I think now your doubt got clear. Like why I begin with stack pointer equal to 16 in push operation. Okay, because when you are popping each and every element from your stack, okay, so we are continuously adding hash code for SP exactly. So when you are eliminating or when you are popping the last element which is equal to 100 at location 12, okay, so after popping that, you need to add hash code for SP exactly. Because of that, we are getting 16. Okay, so I hope you got what exactly this instruction states. Okay, so later, next. So instead of writing these multiple lines, okay, for push and pop operation, okay, we can go for writing single line code exactly. Okay, so what is that? Just observe. We are having push. Okay, so we are using auto increment and auto decrement over here. Okay, for push operation, we need to subtract, right? Fine. Before we are shifting the value for a stack pointer location, we need to subtract. Okay, so post subtraction we are having. Okay, sorry, pre subtraction we are having. Okay, but here in case of pop, post increment we are having. Okay, this is decrement, this is increment exactly. So now push move new item comma minus SP. SP should be within a bracket. It means that, so whatever the SP value you have, like address, it should be decremented it by 4. Okay, decrement means 4 exactly, because it will in case of address, decrement means 4 exactly, because we are targeting for 0, 4, 8, 12 and all. Right, increment means 0 to 4, 4 to 8. Okay, decrement means 8 to 4, 4 to 0 exactly. Difference will be 4. So we are considering it as what? Decrement means decrement by 4 exactly. Okay, same thing we are performing. Here subtract hash code from a SP, then later move the new item to the SP over. So here also subtract it by 4 first, then move the new item. Both are same. Clear? Then what about pop? Say first what I need to do? I need to access the location first, then I need to add. Okay, so because of that, we are having like post increment. So here pre decrement we had, but here post increment we are having. Okay, so these two line is same how we are explaining about this push operation and pop operation using these 4 lines exactly. Okay, so here we are using immediate addressing mode and indirect addressing mode, but here we are using indirect addressing mode and auto increment and auto decrement concepts. Okay, so now we got one condition over here: safe push and safe pop. Okay, safe push and safe pop itself. Okay, sorry, safe push and safe pop. So our job is here. So this is what the stack we got. So 1500 is the initial one. Okay, later it continues till the bottom. See, the bottommost is having the address called as 2000. Fine. What we need to do is we need to design a program, okay, which should intimate the user, okay, if he is in this particular location. Fine. Okay. If he is already pushing some value for the 1500 location, and in the next cycle, if he is trying to push some more value, that will be called as the overflow, right? The maximum capacity of your stack is between 1500 and 2000. Okay, 1500 and 2000. Okay, but here, if user try to insert few more values, if it is already full, then we should get an overflow error, or a full error we should get. Okay, you're getting right. Then later, if you are at this position like 2000, okay, after popping each and every element, you will be coming for 2000. Okay, after popping this element also, if user is trying to pop few more element which is no longer existing in your stack, okay, then we should get empty error. Clear? When your stack is full, you should get full error if user try to push some value more. Okay, and when you are facing the empty stack, okay, if the user is trying to pop the element from the stack, okay, then we need to get empty error over there. Okay, how we can do this? So here we got two references over here. Starting we have and ending also we have 1500 and 2000. Okay, so so that is what we are trying to avoid over here. To avoid the empty error and overflow error, what we need to do, we need to consider an example, okay, which with a stack, okay, which starts from 1500 and ends at 2000. Starts at 1500 and ends at 2000. Okay, condition is when HP reaches 1500, okay, only one element can be pushed. After reaching this point, okay, only one element can be pushed. When SP reaches 2000, only one element can be popped. Okay, if stack point is pointing for this particular location, obviously we can enter one value over here. If stack point is pointing for this particular location, obviously yes, we can pop only one element over here. For this, we are using one keyword called as a compare instruction. It is okay. So here, the gesture of this compare will be compare source comma destination. Okay, anything it may be. So the value of destination will be subtracted with value of source exactly. The difference, whatever we are getting, that will be the return value. Clear? Compare source comma destination. Like compare A comma B means B minus A we are performing. Right? Compare A comma B means B minus A we need to perform. That's why we are writing it as source comma destination. That is nothing but destination minus source. Okay? So that is what compare statement states. Okay. Now we'll go through this safe push. Okay? Safe push. Here, okay, fine. Safe push, right? Okay. So if some value is already residing, okay, let me take one example. Fine. Like if it is 1500, then here it will be 1504, right? 1504 XYZ. Okay, we are having some value XYZ. Then your stack pointer will be pointing for where exactly top of the stack, right? Now, if I want to insert any value, then I can. Okay, no problem. Now, what I need to do is here, first thing, compare hash 500, which is what the topmost element of the stack. Okay, if I want to enter. Okay, so now stack pointer is pointing for where exactly 1504, right? So we need to compare hash 1500 comma SP. What is SP value? 1504 exactly. Compare return value will be what? Destination minus source. What is destination? 1504. What is source? 1500 exactly. What is the difference we are getting? Plus 4 we are getting. Right? Okay. Plus 4 we are getting. Okay, fine. Then we are checking for some condition over here. Branch, if it is, means whatever the return value we are getting over here, if it is less than or equal to 0, if it is less than or equal to 0, we need to get a full error over here. Whether 4 is less than or equal to 0, no. Okay, it means stack is not full right now. Okay, there is some element, okay, or there is some space where we can upload elements over here. Getting or what? Okay, so now what we did, we are comparing the present stack pointer with the maximum capacity of the stack over there. Okay, that is what the 1500. You are at the 1504. Okay, difference is what? 1504 minus 1500. So difference is what? 4 exactly, right? Which is a positive number. It is greater than 0. So this full error will not be encountered. Okay, so instead of that, what we do, move new item where we are having that new item. Okay, example like which is equal to 100. Okay, new item which is equal to 100. So this can be shifted to here. This can be shifted to new item value should be shifted to where first you need to decrement the stack pointer. If I decrement the stack pointer, your stack pointer will be pointing for 1500. Okay, so to this location, I need to shift the new item only. What is that new item? 100 exactly. Okay, now where your stack pointer is pointing for 1500. Now again, if you are trying to push some value, observe it carefully. If again user want to push some value for the stack, now compare hash 1500 comma SP. What is SP value? 1500. What is you are comparing with? Source value 1500. 1500 result you are getting is 0. Okay, what is the branch statement? If branch or else if the return value from the previous line, which is equal to 0, okay, whether we are comparing it with whether it is less than or equal to 0. Yes, it is equal to 0, means we are getting an error message called as a full error. Okay, so from this example, what we can do, we can avoid the overflow of this stack. So same, okay, what we are doing, we are going to check for the safe pop. What does the safe pop stand for? Okay, so whenever we are finding the empty stack. If your user is trying to pop some element from your stack, then you should get a empty error over there. Clear? Okay. So now again, compare hash 2000. Okay, let it be like 1996. Okay, so 1996, you got like 15. Okay, value called as 15. In location 1000, we have double X. Okay, or let it be some integer value itself. Okay, instead of the characters. Okay, so this is what the stack. So here we get 50. Okay, consider like 50 we got. So now your stack pointer is pointing for this particular location. Forget about these two 100 and XYZ. Okay, consider your stack pointer is pointing for where exactly 1996. Now, if you compare hash 2000 comma 1996, what will be the return value? 1996 minus 2000. Return value will be minus 4. Negative value we are getting, right? So now, if branch is greater than 0, we are checking for the condition. Return value, if it is greater than 0, then we are getting empty error. See here. Okay. When we are getting that greater than 0, if you are subtracting destination with the 2004, okay, destination is what? 2004. Source, if it is 2000, then difference will be what? Plus exactly. Greater than 0. Then you are getting the empty error. But now what you are getting? Negative value you are getting. That means, okay, still you are not yet reached with the base of the stack exactly. Okay, if this condition satisfy, then we are going to pop the element. Clear? Okay, fine. Okay, fine. Greater than we need to get, remember. Okay, if it is not, in case of this, we are not finding the empty error. So here, okay, I think you are not able to observe this. So this is what a move, I'm overwriting over here. Move SP plus comma item. Okay, so here we have a statement. Okay, I think the size of the PPT is like bit wide. Because of that, the last statement is half visible. Okay, so I'm just writing it over here. That is move SP within a bracket plus comma item it is. Okay, which means I need to move the stack pointer where it is pointing for 196. So I need to move this particular value from this particular location to item exactly. Meanwhile, what I need to do after accessing this location, okay, I need to increment my stack pointer. Okay, so if I increment my stack pointer, now your stack pointer will be pointing for 2000 exactly, right? Your stack pointer is pointing for 2000 exactly, which is the top of the stack right now. This is the top of the stack right now. Clear? Okay, so now your stack pointer is pointing for 2000. Again, we are comparing it with hash 2000. Observe it carefully. 2000 minus 2000, 0 we are getting. What is the condition? If it is greater than 0, it is not mentioning like equal to. If it is greater than 0, then only empty error. Now, it is not greater than 0. Again, we need to move this 56, okay, value to location item. Along with that, I need to increment my stack pointer value. So now, your stack pointer got incremented from 2000 to 2004 exactly, right? So now, if user again try to pop, okay, so again, same statement, compare hash 2000 comma 2004 now. So 2004 minus 2000, result will be what? Plus 4. Is it right? Plus 4 you are getting. Means branch is greater than 0. The return value of this compare statement is positive, which is greater than 0. So we are getting a error message called as empty error. Yeah. So this is how we perform stack push and pop operation. Usually we are calling it as safe push and safe pop. Okay. So these are the lot of functionalities which is available in our stack. Okay. But when it comes for queues, okay, we don't have much flexibility as we are comparing with the stack. Okay. So we are going directly for the stack concepts. Okay, from further classes. So queues data are stored and retrieved from a queue on a first in, first out FIFO basis. Okay, who will be coming first? Who will be going out first? In case of stack, who will be coming last? He will be going out first. Okay, so there are two important difference how stack and queues are implemented. Okay, in case of stack, we need only one pointer, stack pointer. But in case of queues, we are getting like multiple pointers, like 2 pointers are expected. Why? See here, like why we need that like one pointer in stack? The stack need only one pointer as one end of the stack is fixed. Okay, the bottom will be fixed always. Remember. Okay, top will be varying, right? Sometimes bottom will be the top. Later one more element if I push, then later next element will be the top over there. Like likewise. Okay, when we are popping the element, the stack pointer will be varying over there. Okay, but the bottom will be fixed always. So we need only one stack pointer over here. Okay, while the other end rises and falls. Okay, as data are pushed and popped. Okay, so one stack pointer is enough. Okay, we already discussed. Okay, one with one pointer. Okay, but in case of queues, need two pointer as data are added by one end and retrieved by other. Okay, from one end we are adding, from another end we are retrieving. That's why we are expecting 2 pointers over here. Okay, and in case of queues, observe it carefully. Queues don't have growth control. Queues would continuously move through the memory of a computer in the direction of higher address. Okay, so solution is to use circular queues. Okay, or circular pattern. Okay, so if you are using the queues concept for managing this subroutine concept, then we are facing some difficulties like we don't have a growth control in case of a queues. So it will be continuously moving towards the higher address. Okay. So if you are trying to implement the concepts of subroutine using a queues, then better to go for circular queues. Okay. So these are the few complexities what we may face when we are comparing this with the stack. Yeah. So to avoid this, what we do, we are going for a stack itself. We will be using the concepts of stack for managing the subroutine. Yeah. Okay. So this is it for now, students. So we'll meet in next class with a very important topic called as subroutine. Thank you, students.